Well, here I am. Here I am, the last guy between, I am the last one between you and the food. So, and my wife, Kitty, who some of you may know, cheekily asked me, well, what are you going to be speaking about, Bob? And I said, oh, about spent fuel from reactors. She said, oh, is this going to be a 4-day marathon? And I said, no, I think they might get it in 30 minutes. So anyway, as they say, put your trays in an upright position, fasten your seat belts, and off we go. I don't need to dwell on this. I think much of this was presented yesterday. The Fukushima accident clearly demonstrated the dangers of spent nuclear fuel storage. The explosions exposed the pools themselves, showed how shoddy construction was, and that they basically are warehouses never intended to hold the quantities that they are now holding. This is something I borrowed, or some artists may call it stealing, from Gordon Edwards. And Gordon provided, I thought, was an excellent explanation as to why these spent fuel pools pose greater dangers. Each pool contains irradiated fuel from several years of operation. It contains several cores, not just one core from a reactor. They do not have strong containment. They do not have the secondary barrier of concrete and steel. In the United States, we have spent fuel storage in buildings that you would find at big box stores and car dealerships. Several pools are now completely open to the atmosphere. These pools of this particular design are 100 feet above the ground. And now that the structural integrity is of serious question, further aftershocks and quakes might cause drainage or toppling of the pool itself. Once the water starts to drain, you have to understand that after a point at which the water drains, the radiation levels become so prohibitively large that they will actually prevent emergency crews from actually intervening, because then you're getting at lethal dose rates on the order of 500 R per hour at maybe 50, 60, 70 yards. And that the loss of water could result in the overheating from decay of the fuel, which then cause melting and then what's called a exothermic reaction or spontaneous fire of the zirconium cladding or the metal tubing around the fuel, which could then result in a large deposit of radioactive material. When I was in the Energy Department, we looked at a spent fuel pool problem at the Hanford site, and that had been ignored for decades. And at the closeout briefing, we asked, well, what would happen if there was an earthquake and the water drained and there was a hem and a haw and hem and a haw? And finally, some old-timer basically said, well, there would be a fire that would make Chernobyl look like a pimple on a pumpkin. Irradiated fuel. This is what a spent fuel element looks like. It's extremely radioactive, as some of you all know. Being anywhere near this, you'll receive a lethal dose. These materials are radiotoxic. We've heard a lot of explanation about what that means. But I think there is official recognition by the United States government itself through the Government Accountability Office, who considers spent nuclear fuel to be considered one of the most hazardous substances on the earth. And what I want to talk about is essentially the environment, safety, and health burden which has been imposed upon us that we have to start taking seriously from this detritus. I'm not going to be talking about health effects. I'm not going to talk about radiation risks. I'm just going to talk about the detritus. The spent fuel pool at Fukushima number 4 contained roughly about 37 million curies of cesium-137, or of long-lived radioactivity. I take that back. And about 10 times the amount of cesium-137 that was released by the Chernobyl accident. This should be a very, very high priority. It's not going to be easy. This is not simply getting a crane in there and lifting it out as if it's some sort of cargo on a ship and putting it somewhere else. You're talking about having to lift objects that are on the order of 100 tons You can see that the infrastructure, this is an early photo, a lot of the debris and other things have been removed, and you can now see the top. But the basic infrastructure that allows a safe movement and removal of the spent fuel was destroyed. It has to somehow be restored. All the spent fuel has to be done underwater with nuclear safety rated cranes, and it has to be transferred into a network of other pools. And what you'll see here is what I mean to say is that this is a typical pool setup for a boiling water reactor. It isn't just one pool. You'll see it involves an infrastructure, including what's called a staging pool, and then up there is, some people like to call this the upper pool. These are usually kept empty and are filled when they start to move stuff in and out. So this infrastructure somehow has to be replaced and refurbished, in addition to having a crane somewhere outside that building, in addition to shoring up the structural integrity of this building. We don't know the condition of the racks. We don't know whether the damage of the racks is such that the fuel assemblies are stuck, and whether that's going to be a problem. But assuming everything moves swimmingly well, you're looking at a rate of transfer of somewhere on the order of there's about 1,331 assemblies. If we're lucky, we're moving probably 9 or 10 assemblies at a time, and that takes quite a bit of time and effort. So then those assemblies will have to be put into some sort of dry cast, thick-walled concrete and steel container. That's going to have to dry out. It's then have to be lifted up by a very large crane, placed in some sort of transport facility, and probably moved to the central pool, where they have to thin that pool out because they don't have enough room for the spent fuel in the radioactive ruins right now. This is a layup for a pressurized water reactor, and you'll notice that pressurized water reactors do not have elevated pools. The pools tend to be in buildings adjacent to the reactor. Many of the spent fuel pool storage areas have cavities beneath them, which, if there are drainage and other events, could lead to preferential flow. And again, you see, this is a fairly complex system. This is not just a pool of water with a crane. It involves a great deal of care and transfer through tubes, through cavities, into the pool, and into racks. And there's also, you have to be concerned very much of how you're configuring the storage of these spent fuel pool. You don't just put a batch here and just forget about them. You have to do them in a very specific way, and furthermore, they're now having to do even greater things to do checkerboarding to reduce the risk of ignition. Since the early 1980s, the U.S. Regulatory Commission, with the expectation that the United States would open a permanent repository for the permanent disposal of spent fuel and defense high-level radioactive waste, basically approved high-density storage. These pools are now storing 4 to 5 times more spent fuel than what they were originally designed to hold. The pools were originally intended to be temporary storage facilities for a period of 5 years, and therefore they did not impose or require them to have what are called nuclear safety-rated defense in-depth requirements. These pools do not have secondary containments. Some of these pools have buildings with tin roofs. As I said, some of these pool structures you would find the kind of structure you would expect to find at a Costco, a Walmart, or a Ford dealership. They do not require them to have redundant power. They do not require them to have separate independent water makeup capability. And only after the Fukushima accident did the Nuclear Regulatory Commission get around to requiring the reactor operators for the first time to have instrumentation in their control rooms to tell them water levels, water chemistry, and water temperature of the pools. Before that, people had to go and look in the room. And there were there was at least one occasion when they didn't do that for a while and discovered that the water level dropped dramatically, and there have been some problems. This is a comparison of the amount of spent fuel that, with the 4 damaged reactors, with reactors of the same design, roughly the same design in the United States. You see, and this is by the number of assemblies. you'll see that the pools in the United States have much more spent fuel in them than those in Japan. And that's because they become indefinite storage modes for the nuclear industry because it saves money. This is a snapshot. It took me a while to do this, a slog, but this is a snapshot of what I call the intermediate and long-lived radioactivity of the U.S. nuclear spent fuel inventory. That's based on some rather conservative assumptions. It's based on a 23-year decay time. This factors in the different amount of radioactivity and radionuclides that are generated by the different reactor designs, pressurized water reactors, boiling water reactors. And it also assumes what they call a burn-up period, where essentially the spent fuel is irradiated for no longer than 3 years or 33,000 megawatt days per ton. It's just a snapshot. It's a fairly conservative estimate because since the 1990s, the U.S. Nuclear Regulatory Commission have basically allowed our reactor operators to double the time of irradiating fuel in the reactors by increasing the amount of uranium-235 from 3.5 to roughly 5%. And so right now, the U.S. nuclear power fleet is allowed to operate at the highest burn-up rates in the world. And this is really motivated by economics and not necessarily by waste management. There are now some questions being raised. In the summer of last year, some of the engineers from the National Research Council put this in their magazine. It said the technical basis for the spent fuel currently being discharged, high utilization burn-up fuels, is not well established. In addition, spent fuel that may have degraded after extended storage may present new obstacles to safe transport. This is to give you an idea of what I mean to say when you get high burnup. This is just a comparison of the generation of cesium-137 from the previous level of burnups to the current level of burnups, looking at the different reactor designs. And this is very important because we're now getting into matters of decay heat and thermal heat. We've talked a lot about radiation, but for reactors and for reactor storage safety and disposal, the safety of permanent disposal, a very, very key factor is thermal heat that is given off by decay. Strontium-90 gives off nearly 1 watt per gram. Cesium-147 about 0.42 watts per gram. This is a lot of heat being given off, and this has a lot of implications. I won't get into details because of the time that's up, but what I will say is that they have been observing elongation of the cladding, the thinning of the cladding. The fission gas pressure inside the cladding is 2 to 3 times higher. They are experiencing much greater hydriding of the spent fuel cladding itself. And the reactors, some certain types of reactors are experiencing rather large amounts of what's called grid-to-rod fretting from these high burnups simply from rubbing on the grid. There is more debris that falls into these reactors. Are not pristine environments. They have debris, they have parts, they have bolts, things that fall in on them. They're churning away, they're vibrating away, and they will cause a lot of wear and tear on the cladding. We're talking about cladding, by the way, that is between 0.04 millimeters and 0.08 millimeters. What does that mean? Think about extra heavy-duty aluminum foil. That's how thick the cladding is surrounding the pellets. So this is a fairly important issue. This is a projection that was done by the Nuclear Energy Institute in 2010 of how much spent fuel they plan to be generating and how much they want to keep in wet storage. This scenario basically looks at they're going to be maintaining wet storage until the bitter end of these reactors at high density.